seminar.
Hi everyone, welcome to the High Energy Seminar. Our first speaker today is Dr. Federico Fraschetti. Federico is a staff scientist at the University of Arizona, and he's visiting CFA. He's going to be here until January 2019. And so Federico got his PhD in high energy astrophysics from University of Credo, Italy. And then he did postdoc at the Brera Astronomical Observatory and the CEA St. Clair and Observatory Paris Bourdeaux. So today he's going to talk to us about the application of magnetic field as the inward shock of Supernova Remnant case.
Thanks for the introduction. Okay, I hope can you hear me well. So thanks for coming and respect such a huge crowd. It's a pleasure. Hopefully not only for the pizza. Okay, so I'm going to present a work recently done modeling some feature observed with Chandra in Supernova Remnant Cassiopeia A. I want to stress that this observation wouldn't be impossible without Chandra, so it was really crucial to have a monitoring over a long period of time, in this case 15 years, of the Supernova Remnant. Here I list, I can use the cursor here. Here I list the number of collaborators which accompanied during this trip. So the overarching goal here is to understand the interplay between energetic particles, which we know because we have several information by different systems confirming this, between charged particles which are accelerated at astrophysical shocks in different environments, both interplanetary medium, but also astrophysical shocks coming from the supernova explosions, and the dynamic of the magnetic field. So the real goal is to see what is the fraction of energy which is channeled in these two main contributors, what is the effect in terms of changing the structure of the shock, and ultimately what is their contribution in what we observe in X-rays. The outline is basically given by 3 points. The first one is that X-ray observations identified in the last 15 years, fast variability of a number of regions in different supernova remnant in X-rays, and still puzzling what can produce such a fast variability. The second is a general point, reminding the fact that shocks, not only the ones in the interplanetary medium between the Sun and Earth, not only the ones in supernova remnant, but also the one recently discovered in outburst of novae, might significantly produce energetic particles. But they can also generate turbulence in the downstream medium. So both effects are probably crucial to understand this X-rays observation I'm going to talk about. The last point is that there is a recent multi-epoch observation by Chandra of the supernova remnant Cassiopeia, which was shown in fact in the first slide, this one, which we for the first time quantitatively explained using directly ideal MHD. So we exited from the realm of phenomenologic explanations using scalings between different quantities related to particle acceleration or synchrotron cooling, but we really applied ideal MHD, and we found quite surprising consistency with data, as I'm going to show. Okay. This puts 2 main ingredients that I'm going to touch. The first one on the left is the cosmic ray spectrum observed at Earth over, as you can see, a huge range of energies here. The contribution up to the knee, approximately here, is very likely due to galactic sources such as supernova remnant. That's because the rate of 1 per 30 years and the typical energy of 10 to the 51 erg supply enough power to sustain the galactic cosmic ray populations, even if, as I was mentioning before, the contribution of novae might play a role also in this energy range. This is just started, so we will have to investigate this both theoretically and observationally. The part of the highest energy part beyond the knee is very likely due to the extragalactic sources, but I'm not going to touch this point. On the right, you see the power spectrum of the density fluctuation of the electrons measured in very different environments, and you can see that it follows approximately a straight power law, that what is called the great power of the sky, which is basically well fit by Kolmogorov power spectrum. The point of this slide is that supernova remnant shock cross media which are inherently turbulent, as shown here. So this is the turbulence in the interstellar medium which these shocks have to travel through. And this turbulence is crucial to determine the property of diffusion of particles which are accelerated at the shocks. So there might be turbulence generated by the cosmic rays, that's certainly true, but we cannot neglect the effect of the turbulence which is pre-existing and which is traveled, which is crossed by the shocks. This is one of the most spectacular examples provided again by Chandra of multi-epoch observations of supernova remnant. This is the name of the remnant, and what was surprising, this was published already a while ago, 2007. What's surprising is that if you look at these boxes magnified here and here, it was seen the sudden brightening of hot spots, for example this one, and their very rapid fading over time scale of a few years. You can explain this only if you assume, of course, that this emission is coming from synchrotron, but only if you assume that there has been a fast particle acceleration and the ambient magnetic field is strongly amplified, so of the order of 1 milligauss. And I remember that the galactic magnetic field background is of the order of 3 microgauss, so it's an amplification of several hundreds. And important to keep in mind in this talk is that the scale of these spots was of the order of 0.01 parsec here. So now I'm going to Casey. In this institute already there has been quite spectacular proof of brightening of filaments, for example in the northeast filament shown here in these white boxes. This is in correspondence of the approximate position of the forward shock. There is an image from NuStar showing here the forward shock and here the reverse shock. And again, this rebrightening was occurring on time scale of just a few years, between 2004 and 2007. So going to different point of view, still looking at the same filament. This is an image showing in particular the color coding of this quantity, which is the ratio between the spatial diffusion coefficient and the value of the Bohm diffusion coefficient, which is considered to be the lowest limit of kappa, the spatial diffusion coefficient, which is realized when the mean free path against the scattering over the magnetic fluctuation is not much larger than the gyro radius of the particles, but becomes comparable to that. So in that case, you cannot have just have much more scattering than that. And you can see that this kappa over kappa b is typically much larger than 1, but it approaches the value of a few units or 1 only in this filament and here. So this is certainly it can be certainly considered a proof of the fact that there is a very strong, very short diffusion time scale, so there is a very efficient diffusion. But you can look at this in a more general way, which is that this is just an evidence of a very strong turbulence. As an example, I show here this diagram, which shows different components of the diffusion tensor. So here you are considering different inclination with respect to the average magnetic field. Kappa parallel, which is the one considering here, is typically going down as you increase the turbulence. Here the value 1 is the one when the power of the turbulence is equal to the power in the uniform field. is typically larger than 1, it approaches 1, and it stays for arbitrarily larger turbulences. So you can have this value close to 1 also for if you consider another inclination. So if you look at this diffusion coefficient terms, which are the ones perpendicular. This map is not done calculating kappa parallel, so I cannot show you what is the value of kappa perpendicular, this one on this map, but I just want to show you that a value close to the Bond value of the diffusion tensor elements can be realized also in different scenarios. And now we come to the specific feature which I'm going to discuss here, and these are the ones described and analyzed in a paper recently published. This one, in particular, you should look at this diagram, which is the which is the image difference in this quite narrow energy band of Chandra between the two images in 2000 and 2014, so across a time of about 15 years. And in the green boxes are represented shocks which, following a measurement of the proper motion in this diagram, are moving inward with respect to us, to the observer. This diagram was done using a quite specific technique called optical flow analysis. I cannot give you the details about of this, but it's described quite well in the paper. And this is done also in the approximately same energy range. So the blue is the outward motion, and the red is the inward motion. And you can see that in this region, more or less everything is moving inward. In all these boxes, I report here the measurement of the flux in the same energy range across these 15 years. And you can see, especially in the W regions, from W1 to W4, that there is quite a spectacular change of the flux of, the order even up to 50%. And there is no really theoretical model which can justify this. There might be certainly phenomenological arguments, but we don't have a real model to feed the data, to explain this data. And after this increase, you also see in all these regions a decrease to approximately the original initial value. Of course, this is when the observations of Chandra started, so we don't know if in all these boxes the flux was still increasing or was doing something else. So we work with what we have. In the observational paper, we provide also an argument to explain the origin of these inward shocks, and it's shown here on the left. So this is the image difference which I showed before, and overlaid you see the molecular cloud for which there is evidence from the CO maps in the millimeter range. So it's very likely that this inward shock is generated when the forward shock, which is this solid circle here, collides with the molecular cloud. And of course everything is turbulent, so you can have different shocks moving in a slightly different direction, but still inward if you look at this part, this region, or this region. So now I come to the idea which we used to explain this flux increase. The idea is the following, explained by this simple cartoon. So here you have again the forward and the reverse shock surfaces, which are certainly not perfectly planar on small scale, and they're certainly not perfectly spherical if you look at large scale. For example, here you see what the shock does. The idea is that the forward and reverse shock are both moving outward, and that's because the remnant is young enough that you still don't see the reverse shock moving inward, which is typically occurring when the remnant is several hundreds or more years old. This remnant is only a few hundreds years old. And also the inward shock moving inward. So I showed before that the medium which is caused by the shock is turbulent, so it's very likely that this turbulence over the time modified, corrugated the surface of the shock, this shock, with certain scales. When this process goes on, the shock is continuing to cross inhomogeneities. And what happens when a ripple shock is coming through inhomogeneity is that different regions of this clump are crossed by the shock at different times. So the material is slowed down at different times, and this imparts a differential rotation of the external outer layer of the clumps while it is crossed by the shock. And you can calculate this, that this really creates vorticity in this outer layer, and thereby creates a very strong magnetic field. This is just in words, but you can do this in several ways. You can calculate this in several ways. The very first time this was done, if you go back to the literature, it's quite a while ago, and it was taking an oblique shock, going through an homogeneous medium, and calculating the vorticity generated downstream. I remind you, vorticity cannot have a jump because you cannot have vorticity upstream of the shock, but you can generate vorticity this way. This is indeed is an oversimplified cartoon of what we are looking at. More recently, two-dimensional MHD simulations show what can happen in the same scenario, and you can see that the ratio between the upstream unperturbed field and the downstream perturbed field, it's very large. Is of the order, this is log scale in color, so this is more than 100 factor in amplification. This was 2D, but was confirmed also later on in 3D. But how can you really calculate this in a predictive way? So simulations confirm that this can happen, but how can you have a predictive method when you go to analyze data, observations? So we know that the jump conditions, the ones from textbook, ranking Newtonian jump condition, can be applied only if the shock is infinitely planar. So if shock is rippled, this just cannot be done. Simply, but you can in fact do it if you define a local reference frame which is at every point of the shock surface defined by a normal direction and a tangential direction, and in this reference frame you can calculate how the quantities upstream, the hydrodynamic quantities upstream, are related to the ones downstream. And this happens in the way I just described before. So it's true, you need both ingredients. You need the shock which is rippled, and you need an inhomogeneity upstream to impart this differential velocity and thereby generate vorticity. But I show you, in fact, in the next slide that you don't really need ripple shock to start this process. So this is a cartoon image which shows shock surface here. Here I take just a perfectly ideally planar shock and moving in this direction, so from your right to your left. And it is a clamp. The typical clamps in the ISM have a core. If you look at different models, they are more or less all consistent with having a core with a uniform density in the center and an outer layer where the gradient of the density is non-vanishing. So when the cross goes by this clamp, something can happen because the gradient of the density is always radial, as it's defined by the picture. But the gradient of the pressure is not, because, of course, it follows the shock surface. So on the points of this clamp, the cross product delta rho, grad rho and grad p is non-zero because they are not always parallel, and this creates vorticity. As I show in the following slide, this is one of the terms in the time evolution of the vorticity. To remind this quantity, which is the thickness of the outer layer, given by the thermal instability models of the ISM, and a good value for this is 0.01 parsec, which I remind you is the number I show you in the first slide. So I said that you can calculate this. In fact, you can. So it's not easy, but you can do it. So this is the vorticity generated downstream of the shock, and is given by these three different contributions, highlighted with three different colors. The one in red, contains the gradient of the density, and it's reminiscent of the this grad rho, grad p I showed in the previous slide. So you can generate vorticity even if you don't have a ripple shock surface, but you have an ideally planar shock. Of course, while this process goes on, the shock also will become rippled. And this term is also proportional to the shock speed in the upstream frame CR. So this is really the term which describes how the ram pressure, the kinetic energy of the shock, is converted into the vortical motion downstream. The second part is the gradient of the shock speed along the shock surface. So if you have a perfectly planar shock, this term is just zero because the speed of the shock is the same at each point of the shock. And this also comes back to the previous slide showing that you can have vorticity also at the planar shock. And the last term gives you the back reaction of the magnetic field in the downstream. From this, I'm just keeping a lot of steps, but you can ask, please ask later on in the next few days if you have questions. You can calculate the field which is amplified downstream and is given by this quite simple expression as a function of time. Here tau, the relevant quantity, is the growth time scale of the field, and it's basically given by the ratio between this LF and the shock speed. So it's not really the ratio between the sides of the clamp and the shock speed, but it's more the ratio between the layer of this outer clamp. So this means that the vorticity is not generated by rotating the entire thing, but just in the outer layer. So shearing the outer layer where the density is as a non-vanishing, oh, sorry, that was Alaska, the non-vanishing gradient. So if you take that time dependence of the magnetic field and you calculate the synchrotron emission, keeping all the other quantities constant in time, so this is the magnetic field, and this is the fit of the flux which I showed for one of these regions I showed before, so the region W3. So we're quite surprised to see that this fits so well. I remind you that here the shock speed, the compression also of the density at the shock, which gives the spectral index if you assume a simple power law, and also the photon energy of Chandra are fixed by the observation, so there are no parameters you can tune. So the only real parameters used here are the length scales of the clamps. And these are 10 to the 18 for the radius of the clamp, and a fraction of that, about 0.7 for the region of the outer layer. The value of the growth time, tau, which I defined in the previous slide, is about 29 years, which is much longer than the time window of Chandra. So this means that either the growth of the flux started much earlier, either there is something else which stops the growth of the field, thereby the growth of the flux before, either both. I should say also that this flux increase might be also related to a very slow acceleration time scale of the particles. So that is not the only way you can explain this flux increase. Instead of the growth of the magnetic field, or you can also have another mechanism which with other dependencies on different quantities explains the fact that the magnetic field is growing. Now we come to the flux decrease, which is not explained by the model. In fact, if you calculate the ratio between the time scale of particle acceleration by the shock, given by the standard diffusive shock acceleration, and the synchrotron cooling time, and this energy range of Chandra, you find that this is larger than 1. So this means that the electrons cool much faster than the time they can accelerate. So this is okay for the decrease because it shows that the cooling is happening faster. But using the same observational quantity is not okay for the flux increase because if the particle emit before being accelerated, they cannot really give this flux increase. There is a number of possible factors which can explain this. One is that to calculate this acceleration time, we use the shock speed observed basically now or recently. But in fact, the shock must be decelerating while crossing the homogeneity because of the impact. So And this acceleration time depends over the square of the velocity of the speed. So this gives an appreciable change in the acceleration time. Another possible factor is that the photon cutoff is determined by new star observations, which have a much worse spatial resolution than Chandra. So there is possibly an uncertainty in that. Another factor is possibly that the field can just be dumped downstream somewhere. This you can, we'll test using radio observations. Another possible factor is that the cloud might be also disrupting while the shock, it crossed by the shock, because the time scale of shock crossing is not much larger than the time scale I've shown here. Sorry. So in conclusion, shocks across media which are naturally and inherently turbulent, and this is very important in determining the diffusion properties of the particle acceleration. The monitoring by Chandra of the shock cloud interaction provides really an invaluable information of the dynamics of the shock, and this for the first time we quantitatively related to a model. And the last point is that the turbulence, in fact, I've shown here, scales with the alpha Mach number. And for this shock is less than 10 is relatively small. So this is consistent with the fact that you don't expect a huge amplification. As I showed before, the amplification is relatively small. Okay, I think I stop here.
You did not in any slide mention the properties of viscosity or what you're assuming about viscosity. In other words, you're completely negliging fluid properties of the matter in the supernova expansion shell. Can you justify that? Because you talk about turbulence, but I don't see you estimate a Reynolds number and tell us what the turbulent Reynolds number is, or having to do with fluid properties.
Well, this is the field grows through a dynamo process. So you can calculate this without specifying the Reynolds number. And all this is done in an ideal MHD also. So might be that these scales, the viscosity is not important. These are the scales I'm talking about are a good fraction of a parsec, so they are not very small. So this might be.
If you have this inward shock, that doesn't necessarily mean that the shock clumps are moving inwards. They're still moving outwards. So I would think that apparent inward motion is really a phase speed showing the position of the shock rather than the velocity of the pulse. And then it becomes unclear to me what the growth time of the brightness means.
Well, what I've shown is assuming that the clumps is in the shock layer, so which is moving outward. So it's not the only option. You can have also a shock moving more inside in the unshocked ejecta. So in that case, the speed will be different, and also the growth time will be different. But in that case, the compression and the power law index of the electrons was very steep. Was 2 units lower than in the case I've shown. So it's maybe unlikely that one can have high energy electrons there.
Okay, let's move on to the second talk and let's thank the second speaker is Dr. Tony Stark, and he's an expert at Center for Astrophysics since 1991, and he got educated at Caltech and Princeton, and One and CO service. And he was one of the founders for the Center for Astrophysical Research in Antarctica. And he's now he's been the co-PI of the Transport Telescope, which has been operating for 10 years. And today he's going to talk to us about some recent results from the Transport Telescope.
Okay.
Just a microphone.
Oh, got the microphone. Nice. Oops. And clip that on there, up here somewhere. Great. Yes, broken bits of equipment. I'll just put that in my pocket. Okay, well, so this is a report about the current status of the South Pole Telescope. I'm going to try to skip over a lot of the introduction because hopefully a number of you have seen this kind of stuff before in the last 10 years. I'm going to report on mostly the things that I've been doing and just kind of skim over what's coming. But it's all going extremely well. I would like to remind everyone that this project started in some sense here. Originally it was me and 3 other guys. And this is a conceptual drawing produced by our central engineering department 20 years ago. This is what we've got now. So 170 publications later, and now the consortium is something like 85 people at 23 institutions. So it's gotten to be quite the big deal. Here's a look at the dark sector of the South Pole. This is looking from the new base, and here's South Pole Telescope and the BICEP and Keck arrays. And the ice cube is somewhere over here in a cubic kilometer. Here's an aerial picture of what's going on. So the SPT is over here in this lab. There's an older lab that's nearly buried here, and my old building for the Astro Telescope is now totally gone. Ice cube is around here, and this is the main base and the new structure for the base. The old dome is gone, and they're eventually getting rid of all of the storage capacity here. This is the runway. So ski-equipped airplanes land there. The South Pole itself is actually right about there. And South Pole Telescope always seems to be in the picture since it's the biggest thing around. One part of this story is that the number of detectors is going way up, and the detector that we have on that we've just gotten going is this SPT-3G. SPT-SZ was the original system put on in 2007. It had fewer than 1,000 detectors, and all of that stuff is now published. We're kind of working on cranking through SPT Pole, which was our first detector system that was capable of measuring polarization and therefore B mode. So in some sense, we were the first to see B mode polarization of the CMB. And now we're working on SPT-3G, which I'll talk about quite a bit in this talk. So in these observations, all of the stuff in the elevation structure is static. There's no choppers or anything. And we simply scan in azimuth with the whole telescope at a rate of 10 degrees in about 3 minutes. That's kind of variable depending on what scale of the CMB you want to look at, right? Because what you're really doing is comparing a few microkelvin over here to a few microkelvin over there against a background of about 20 Kelvin. So it's much easier to measure if you're very close than if you're going fairly far, and that's one of the subtleties of this whole deal. So this is an example. People think Planck is wonderful, but this is the same piece of sky observed with WMAP. Here it is observed with Planck, so that's, it's pretty good. It's, totally independent measurements. And here it is with SPT pole. We are 6 times deeper than Planck in SPT pole. With the SPT-3G detector, we are going to get down for some pieces of the sky 30 times deeper than Planck. And we also have, in some sense, 9 times the resolution of Planck. So it's really a lot better. And for the, we can't, of course, see the whole sky. We can only do our best work on about 10% of the sky. But that's pretty good, and we can do a way much better job. So there's a bunch of things here that you don't see in the previous pictures. For example, this is a Sanyo-Slavich effect. These are either AGN or very dusty galaxies that are peaking up in the as point-like emission features, where point-like here means that in this picture, they're an arc minute across because our resolution is still around 1 arc minute, given that it's a 10-meter telescope and working at 3 meters wavelength. So this is a filtered version to get you closer to those point-like objects. And the things we see are primordial anisotropy of the CMB. In this case, this picture is effectively noiseless. So what you see in the CMB here has got a signal noise of around 100. And another thing we see are active galactic nuclei, and some of them are lensed. So active galactic nuclei that happen to be lensed by an intervening cluster or an intervening galaxy are particularly bright. And in that way, we can get a look at high redshift objects that are normal, because this brightening can be a factor of 20 or 30. And so that gives you sort of a speed increase of 1,000 almost compared to what would otherwise be the case. So you can kind of get a look at normal objects at the very high redshift. And then there's the Sanyo-Slavich effect. And if you look at one of these spots, with the Sanyo-Slavich effect, you don't really know what redshift these objects are, because they basically look the same at all redshifts. And to get a redshift, you actually have to look in the visible and start doing optical studies and spectroscopic studies and with optical follow-up. And then if you, of course, as our Chandra colleagues here like to do, look at this in the X-ray, and these are all X-ray objects as well. So there's various SPT surveys. The surveys are more or less coincident with the dark energy survey footprint. We now are doing, in the summer, we have to kind of go around to the other side of the Milky Way. So this is the near the southern galactic pole, but we also do some work in the other hemisphere in the summer, just because we can, and it gives us, it's not as accurate and it's hard to go deep, but you can certainly see the massive clusters. I'm putting this up because it's a cool picture, if a little ugly in its choice of colors. This is a combined, the very first combined data set from Planck and SPT. So the low spatial frequencies are done with Planck, and that map has been, in Fourier space, has been combined with the Fourier space higher spatial frequency part from SPT. the whole thing put together in the Fourier transform space and then retransformed into a map. And so this is a map of the Large Magellanic Cloud, and it's got, the 30 Doradus region and all of this dust. The dust is showing up as bright because the high frequency short wavelength is red here, and so the dust peak at 100 microns going out to 300 microns is bright in these star forming regions, and then this background, which unfortunately looks kind of muddy, is microwave background, and then a few synchrotron sources here and there which haven't yet conked out at this very high frequency, and this is probably a background source. So I think that's pretty cool. There will be many more Planck plus SPT images coming out in future. We've got some of, there's one of the small Magellanic Cloud. This is all published, so it's in this paper by Tom Crawford in late 2016. Okay, SPT science. This is like all the stuff I'm not going to talk about anymore in this talk. But several types of science. The main one is CMB properties, CMB polarization, the MC fitting of models to the CMB as observed. This, as I mentioned, discovery of high redshift lensed galaxies, and then the discovery of clusters of galaxies via the Sanyo-Zildovich effect. When you go fairly deep and you're working in Sanyo-Zildovich effect, you can essentially find all clusters at all redshifts. So you can, in an area of the sky, you can do an absolutely comprehensive catalog of all clusters at all redshifts as long as they've got ionized gas in them. And as we'll see, we're getting up to pretty darn high redshifts now, redshifts of 2 and even a bit more than 2. And found by this method, we found a couple of protoclusters that are redshift of more than 3. And then finally, the SPT is an important element of the Event Horizon Telescope. So this is this world-spanning interferometer that's looking at the black hole in the galactic center. So every once in a while, we take down our big microwave background receiver and put in a single heterodyne receiver and combine it with all of the other detectors. And it's an important station because it's the southernmost station and therefore gives the north-south baselines that you really need in that direction. So, important instrumental point, this complicated thing is just the progress in bolometers over time. And we've now gotten to the point here, the important point here is that we've now gotten to the point where the detectors are background limited. That if you got rid of the small amount of ground pickup and the noise from the atmosphere, which at the South Pole is quite low, you would essentially be much better off. So potentially you could do much better in orbit. But on the other hand, these very sensitive systems also require temperatures of around 100 to 200 millikelvin physical temperature of the detector to operate, and that is not impossible to do in an orbital system. But for example, our system, SPT3G, we are constantly expending 15 kilowatts just keeping the focal plane cold. And so that is hard to come by in space, and this is why we're doing so much better than any other instrument, and will likely be the premier instrument for the next decade, because the sky at the South Pole is really not too bad, and we have these background limited detectors. Yes?
Tony, do you have to subtract off a foreground halo model for the results that you quoted here on SZ effect and so on? The foreground that...
Well, there's lots of foregrounds.
The galaxy halo.
Right, that's why we do multiple frequencies, is the foregrounds get fitted in spectrum, right? So the microwave background has its spectrum, and the foregrounds have their spectrum, and so you can pull them apart by observing a multiple frequencies. And this is done by all CMB instruments, and that's how we get clean off the background. Yeah, the data reduction of this thing, using an array processor of some hundreds of cores, you can process a month's worth of SPT data badly in 2 weeks. So the data reduction algorithm is not even optimal, and we can just about keep up with it in real time. So anyway, the point of all this is that individual bolometers now cannot be made any better as far as we are concerned, and the only thing that you can do to make things more sensitive is to have a lot of them. And so we've gone from the original SPT 960 detectors, the SPT 3G is 16,000 detectors. In each one of these pixels, there's 3 different frequencies at 2 different polarizations. So each one of these little spots is actually 6 detectors. And what is politically coming along is this stage 4 business where people have realized, oh, what we really want is like 1 million detectors on the sky. But on the other hand, if you have merely 10,000 detectors, you can do what you would do with 1 million detectors in only 100 years. So it's a matter of trade-offs. A lot of what is claimed for this could actually be done with this, but over a longer time scale. So that's kind of a political issue. Here's what the detectors look like. They're these funny multi-wavelength planar antennas, and then the actual detectors are sitting in these strip line configuration things at the 2 different polarizations at different wavelengths. And so each little bolometer like this is one of these things on the hexagon. Then you put the hexagons together into a focal plane. This focal plane is 43 centimeters across, and it is maintained at 180 millikelvin physical temperature, even though it's exposed to space. So that's part of the trick in all of this. And the way that's done, this is the SPT3G optics design. I have to show this because it was designed by Nils Hammerson and myself. And in fact, the final as-built version is my final design. So what's happening here is you've got the primary mirror out here, prime focus of the off-axis telescope here, a warm secondary mirror that's made of aluminum, a warm flat tertiary mirror just because due to what's called the Dragoni relation, this whole thing really wants to be up here, but then it would be in the way of the beam coming into the primary mirror, so we put in a flat mirror. And then we've got this re-imaging system, which it's actually, as an optical design thing, it's absolutely miraculous because each of these lenses is doing like 2 jobs. And I was utterly astonished that this thing actually works. These lenses are made of alumina, which is, of course, an oxide of aluminum, and they are huge. I mean, they're 55 centimeters in diameter and weigh the better part of 100 pounds. So you have re-imaging onto a Leo stop. So everything from here back, this stuff here, this, and this are cooled to 4 Kelvin, and then this is cooled to 180 millikelvin. And that is done with this big Dewar, which is actually about 7 feet high, so it's twice as big as it appears on the screen here in real life. And here it is. Here it is actually installed. So there's the primary mirror out here. This is that warm secondary, the warm flat, the big honkin' doer. In our design, we're going with one big camera with one big focal plane. The ACT people, who are our competitors in Chile, have taken a different approach, which has its own benefits and disadvantages, where they have a number of different tubes looking at the same focal plane. So they have separate vacuum systems and separate optics, and they don't have to have such big lenses. But we're able to really exhaustively tile the focal plane with detectors. And in some sense, this is the ultimate optical design that you could have with this telescope. The field of view is over 2 square degrees, and that's about as good as it's ever going to get. So we might be able to cram a few more of these hexagonal tiles into the bottom of this doer, but we pretty much got where we're going to get. This has all been delayed by, it was kind of a year and a half late, but as of now, we have 11,000 bolometers which work to specification. So we're still missing about 5,000 bolometers. These things are very flaky. They're superconducting, extremely sensitive little hoochie-madickies, and they just don't always work. But they're all independent. They're all independent measurements of the sky, and so you don't need them all to work. You just need a lot of them to work. And we now have a lot of them actually working, and they are working to specification. Oh, here's that focal plane again. So the point of this is that the mapping speed compared to our original system is now an order of magnitude or more better than the system, which was a factor of 6 better than Planck. So we will, in some sense, be almost 2 orders of magnitude deeper than Planck in the fields that we're studying. And the results of this, in some sense, we're not allowed to say this because one of the things that they're doing for SPT 4th generation is getting the neutrino masses. But as I will show you, we will probably get the mass of the neutrinos first, and with SPT 3G in 2 different ways. We may also do a fairly large-scale measurement of R, the tensor scalar ratio from the very, very early universe. That is the bicep Keck array thing. We have this is a map, right, of spatial frequency. These are small scale, so these are things very close to each other on the sky, and 100 are things that are a degree apart on the sky. And as you go down to 1, you get things that are widely separated on the sky, and that interesting value of R happens at a scale which is a bit hard for us, right? We have a hard time switching that far and making a difference. Bicep is made to do that problem and that problem only. We can kind of get down to that level if we scan very fast. And it wasn't clear until we actually tried it that this was in fact possible, but we now think it is. So we now think that given the atmosphere, given the detectors, given the noise, given the systematics, that we can in fact get down to a value of R in a good many years of observing and do a good job at it. So in some sense, this is the ultimate bit of CMB science. The other thing we're going to get is lots of clusters. So the X's here are our SPTSZ, that very first detector. We detected 530 previously unknown clusters, and those are these black X's. Planck, being a pathetically small instrument, can't detect the ones at high redshift because they're too small for its large beam, right? It's only it's only this big across, and given diffraction, it just can't see these smaller clusters. And then the blue is our predicted detections of with the currently operating system. So we will go deeper. This cutoff here is just artificial. This would say, this is where we don't believe the signal and noise anymore. But going out in redshift and going deeper. So this, this is about 5,000 clusters, and based on our current detection rate of clusters, we fully expect to detect another 5,000 more. Most of them smaller than the ones we've been working on now. So the future of SPT. There's much left to do, and I'm going to, in the few minutes left, talk about the cluster method, which is what I'm primarily working on. And in that, you get one of these detections of a cluster and do weak lensing on it in order to determine its mass. And the idea is that if you had a comprehensive catalog of the actual mass of clusters, that plus the X-ray data would really do your cosmology a good job. And so we've got these multi-wavelength follow-up campaigns, and there's an instrument which was built here, P-scope, by me and Brian Stalder mainly, which is a camera, an optical wavelength camera. So this is optical light and plus near infrared, and the system takes the collimated focus of F11 of the Magellan telescope and breaks it up with dichroics into 4 simultaneous images, and over a field of view that's about as big as you can get with the F11 focus of Magellan telescope. And here's the basic design of it. So these are the optics down here, and they're put in a box, and there's a doer and a cryogenic. Well, it's called cryogenics, but this is getting down to minus 100 degrees centigrade, which compared to the 100 millikelvin of SPT is not really cryogenics. And this is then mounted on the on an F11 focus of the Magellan telescopes. So here's a drawing of it, and here's Brian. So Brian is now installation scientist at LSST, and here he is looking. Here we are looking through the collimator when we had it on the lab bench over at Cambridge Discovery Park. Here's some tests. It's designed to have very small point spreads function, and the point spread function is measured, is pretty good. And here's some tests, and here it is on the telescope. So you get an idea of the size of this thing. It's actually 8 feet long and weighs a ton. Has vacuum systems and a whole lot of electronics and cooling and water cooling and some robotics control, because as it turns in gravity, the things warp, and you have to take that warp out and stuff like that. So it's a complicated camera. In a lot of ways, the best camera, well, over its field of view, which is 9 arc minutes, it's arguably the best camera in the southern hemisphere. And it's on this big honkin' telescope, Magellan. There's another picture of the instrument on the telescope. And here's what it can do. So this was the first picture where it took 1 minute. This is what you get out of one single multiple frame exposure, and that can all be put together into this. So this is a 1 minute picture. Here's an idea of how big those mirrors actually are. Pretty darn big, not as big as some, but really pretty darn big. And again, here's what we anticipate looking at in terms of clusters. And here's some reduced and measured data of clusters. We've looked at all of these things. These things have all been looked at the X-ray, so the bullet cluster we all know about. a bunch of clusters that were actually discovered with SPT and their Sanyo-Slavich signatures. One thing we've done is, whoops, time's up. We now have images of all the SPT-SZ clusters using PSCO, so a uniform sample. And the question is strong lensing, is there more strong lensing than is expected? And I think the answer actually is yes. So this is in preparation. One more thing. So this is the takeaway. In these cosmology things, the red and the blue are real data. And the gray is what you would get if the calibration of cluster masses was within 4%. So the only thing that's keeping the cluster method from being really good and being one of the best cosmology things ever is the fact that we don't really know the slope of the observable thing versus the actual mass, right? It's a very tight correlation with the X-ray data, but the slope is unknown. And the way to do that is by weak lensing. We're doing weak lensing. We've actually published a paper this year with some 30 clusters and got good results. And here's the results. They look terrible, but what you have to realize is that the relation between theoretical or real mass and some observable, this is an X-ray observable quantity as developed by Alexei and collaborators here, that this is actually very, very tight, and what's not known is the slope. And so these crappy weak lensing measurements get you a measure of the slope. In principle, we could do thousands more measurements like this. And so hopefully it will get better, and if it gets better, we will be on those little gray patches instead of on the blue and the red patches, and it'll all be good. So the end.
And then the mass of them decrease, you can measure less massive clusters at higher redshifts. What's that?
Because they haven't formed yet at that redshift, right? Those low mass red clusters at that redshift are still building up, and they will be the massive clusters of today. But but that's 10 billion years ago. Back there, it's ZF2, and so they're just not very big yet.
How do you expect to get the neutrino mass?
Well, it's fit by, the mass of the neutrino affects clusters in a couple of different ways. It starts out as a relativistic fluid, and then depending on its mass, it becomes a non-relativistic fluid at some redshift, which is actually some redshift within the redshift range that we are actually observing. And seeing that transition gives you the mass of the neutrino. And that's the cluster method way of doing it. There is a purely CMB method of doing it, which I must admit I don't entirely understand, and so I'm not willing to bullshit you about it. But the cluster method is basically a transition from a relativistic fluid to a non-relativistic fluid while the clusters are actually forming. And that fluid fills the clusters, and it engages in cluster dynamics, and that's why the number of clusters as a function of mass and as a function of redshift is a sensitive measure of the neutrino mass.
Okay, let's thank Tony.
Oh, that's been great.
Hello, my name is Laura Floyd. I'm a junior